So thanks for joining us, team, and those that have joined us from the region. Just wanted to give a quick recap of why we're here today before I get to introduce Mike Vasquez around the webinar that he'll be hosting. So this is part of the accelerator program out of Industry Labs. Uh, Around accelerators, we're really trying to do three things: bring a cohort of people together around a specific topic, uh, do some demonstrations on that technology, and really trying to break down barriers and create those use cases for the cohort members around a specific technology. Would love to be able to share more about that if anyone on the call is not familiar with the accelerator program here at Industry Labs. But thanks all for joining us here today. Those topics that accelerators are covering right now, you're part of this additive manufacturing team right now, but we also have accelerator around autonomous mobile robots, knowledge generation, offload automation for CNC machines and surface finishing. If any of these are interesting and you're not aware of them, please reach out to me or another person at Industry Labs, and we'd love to share more. So we're here today around additive manufacturing. What we're trying to do, one, is break down some of those barriers of adoption, show some of those latest technology as the world has continued to evolve in this space continuously around additive. We're hoping to do some demonstrations for people in the cohort. We've looked at sample parts. We've provided some sample parts of parts that people are considering getting moving towards additive and showing the state of technology there. Would love to be able to share more about this accelerator after this webinar. Please reach out to me if you have questions, or if you think anything here sparks an idea. We'd love to have a further conversation on it. So before I hand this off to Mike Vasquez to lead this webinar, feel free to ask questions in the chat as they come up. You also have the capability of also unmuting yourself, so feel free to do so. Thanks all for joining us here today. Mike, I'm going to go ahead and hand it off to you.
All right, perfect. Thanks, everyone. Thanks for joining. So like Michael said, if you guys have questions throughout the webinar, just let me know. I don't mind being interrupted. I don't mind kind of putting your hands up or putting questions in the chat. I'll do my best to kind of keep track of those. But I like that if it's engaging and things like that. And I think it makes it more enjoyable, and appreciate you guys joining over the lunch hour. So I'm going to share a handful of slides. I've got a bunch of parts next to me. So if you can see my screen, I'll kind of zoom in on those, just talking about additive manufacturing, specifically in the metal space. So as we started this accelerator a couple months ago, inevitably, I mean, most companies in the region at least are familiar with 3D printing, right? They may have a desktop printer like one behind my shoulder that's doing kind of filament and using it for prototypes and jigs and fixtures and things like that. But a lot of times there's questions about metal and what's the state of the art. Hey, last time we looked at it, it was really expensive. What's changed? What do I need to do to look at it? Is it price competitive? Where should I use it? And so that's kind of the spirit of this webinar, is a kind of whistle stop tour of a number of things. So what is it? What is it? What are the different types of technologies? How much is it? And what are the capabilities from a surface finish? Some of the technical specifications of, hey, can you machine it after? Do you need to machine it? What's heat treating? All that sort of stuff. So that's kind of the spirit. We'll hit that in about 30 minutes or so. Obviously, we can deep dive into any one of these into more detail, but the aim of this is to kind of give an overview, and then for those who aren't kind of directly involved in the accelerator now, oftentimes we'll come on site and talk through more details on this to see if, hey, maybe there's some parts in your in your business that might be a good use case or thinking about kind of future operations. So just a little bit about me. My name is Mike Vasquez. I run two companies. I've been in the additive manufacturing space for about 13 years. So I'm a materials engineer by background, went to MIT and then did a PhD over in the UK at this university called Loughborough, about an hour north of London. And that was all focused on developing materials for kind of production-based 3D printing technologies. And so after that, really decided to focus in on the industry. My first company, 3Degrees, really helped kind of as a consultant about 24 companies set up production facilities where there's multi-million-dollar investments, everything from defense contractors to medical device manufacturers and smaller organizations. So helping them both understand kind of the technical requirements and safety requirements, all the way to finding a business case and use cases as well. So from there, we actually developed some in-house technology. It's a software system that we used for data management and traceability within kind of 3D printing. So when companies look to put a part on a plane, they need to do a lot of background testing to make sure that that's going to be safe and that's going to be available for them or safe to operate. So we have a software that specifically kind of focuses on that. And then we have our second company that's mainly focused on continuing that consulting. We also do a lot of workforce development in the space as well. So yeah, I'm going to kind of keep going. I saw a couple of things come through the chat, so I'll just have those. Okay, can you guys see my screens now? Is that good? All right. So yeah, just keep me on top of that if anyone has any issues. So the 4 or 5 things we're going to talk about today. So first one is going to be kind of market size and adoption, kind of what's the state of the industry, how is it contextualized with things that you normally know. We'll talk about a handful of different 3D printing metal technologies. That's something that most people coming into it don't realize, that there's multiple ways to put metal together in a 3D printed way. So we'll talk about kind of what those look like, and what that what some of the opportunities each of those technologies provide. Then we'll get into some design considerations and kind of what are constraints, what are size limitations, can you machine it, all of that fun stuff. What some of the common materials are, and then just touch on a handful of use cases and just really kind of get your brain going about, hey, where may this fit into my business? So that's really this kind of the overview. And so if I was in your position, kind of things I would be thinking about, if you have specific questions, more just, hey, is this something we should explore? Is it something that we want to kind of look into? Is it not a fit today? Is it something we want to check out later down the road? So here, kind of the first thing I'll kind of cover is kind of where the market is, right? So additive manufacturing generally has been around since the early 1980s. So it's not new. I'm going on 45 years, but that was mostly in the polymer space, and plastic. So for prototyping, things like liquid resin, DLP, that was kind of early days. Metal really kind of took off in the, I would say, mid to late 90s was when a lot of the technology was developed out of the University of Texas. And since then, it's really been kind of the main technology for production parts when it comes to 3D printing. Most adoptions in aerospace and not a little bit in automotive, aerospace, kind of planes and things like that on the defense side, and then also on the kind of space. So if you see any of the like SpaceX rockets that have launched recently, a lot of those rockets are built using additive manufacturing. So impressive kind of use of the technology for kind of low volume, high value parts. But a lot of adoption now in medical spaces, implants, tooling, things like that. So just for some context, these are rough numbers. I kind of always trust these with a grain of salt, but it's relatively close to this. So the broad 3D printing market is kind of about $20 to $25 billion, whereas at kind of the metal space is about half of that. Really driven by some of these production applications, both in terms of how the contextual of like selling materials and printers, but also the end use cases and some of those applications that are being used. It has been growing pretty steadily over the last decade now, kind of in the 20% or so compounded annual growth. There have been some kind of setbacks on kind of more the public marketplace with a few companies that went through the SPAC investment process. Those have now kind of gone bankrupt. A lot of their assets have been sold off, but a lot of the core companies that we think about in the terms of the metal side, companies like EOS, a German-based company, GE Additive, which makes metal systems, Renishaw, a UK company, they've been kind of approaching this growth pretty steadily and over that time and continue to be poised to make additional gains. But this all encompasses a variety of different aspects of the industry, right? So there's the traditional way you would think of a CNC machine, right? There's people that sell the machines, and there's people that make stuff on it. So you can bring that technology in-house. And just as similarly, there are job shops or service bureaus that can provide parts for you. Same thing in metal 3D printing. So there are companies that you can buy printers from and bring the technology in-house. And then there's also a number of suppliers across the country that will produce parts for you. All you have to do is send a 3D model and you can get that produced either at low volumes. So like, hey, we need a 1 or 2 off. There are also some that will take on a full supply chain or a full supply product line and do the quality, do the testing and all that for you. So there's kind of a range in that. But where you think about 3D printing on the metal side, this graph is usually pretty nice to kind of just conceptualize it. So they're not going to be huge parts. You're going to think other than like some of the rocket engines can be pretty tall. So like there are parts that are up to that height and weight, but you're talking tens of thousands of dollars for those types of components. Most parts fit into kind of think of a shoebox or two size kind of build area. And that's where kind of the sweet spot is for metal 3D printing, some of those components. And we'll talk more about that in the coming minutes here. So, let's see. So as I mentioned, there's really kind of 3 different types of printing technologies when it comes to metal 3D printing. And when I talk about different technologies, basically it means kind of how do you put the metal or how do you put the materials together, right? What is the mechanism for sticking whether it's powder, whether it's wire, whether it's molten metal, how does that go together and what are the steps involved and what are the different use cases? So if you come away from one thing today, I would say this is an important kind of takeaway is, hey, there's 2 or 3 different options here. We may want to look at 1 or 2 of them specifically. So the first one is called binder jetting. Fairly straightforward. So the raw material is a powder. It's a powder metal. It's in a bed like this. If you guys can see my kind of cursor, you start with your 3D model. So if those who are kind of familiar generally with 3D printing, whether it's plastics, whether it's metals, you got to start with a digital design, some 3D model, and that is sliced into different layers. And in the binder jet process, each layer is started by depositing it we call it an ink or a binder in this case with a kind of inkjet head. So imagine kind of a type of inkjet head that you use in your everyday printer that's just going out over a bed of powder, and that then fuses powder together like glue, right? So imagine, okay, like I do that a few times, but that's not going to be the same as a finished metal part or a machined part. What you have to do then is once that part is fully kind of stuck together with the glue or with the binder, you have to do a secondary kind of furnace step where you're heat treating it, you're kind of sintering it together, and that binder is either retained or kind of evaporates out, but the metal itself is fused together in that shape. And so you come out with after the inking process, it's a green part. You put that into a furnace or a secondary process, and then that fuses together with your components. So generally, like some of the companies involved in this, HP is a big player on this. They've got a handful of machines out in the wild now that are using this for, I would say, smaller components, like think gears, they're doing a lot in the automotive space, even zippers and things like that are like fairly small. But it's repeatable. You can kind of scale it up, and kind of go from there. The challenge is kind of when you end up kind of fusing the particles together, you could get shrinkage, and dimensional kind of accuracy is a challenge there. So the next one that a lot of when I think of metal 3D printing, this is what I think of is what's called powder bed fusion. So this is where you're literally taking a metal powder and you're welding it together with a laser. So I'll play the video, and you can kind of see what that looks like. But basically, again, it's a layer by layer process. You've got a laser that's outlining kind of each individual kind of part, and it's literally kind of a weld. You're welding it to a build plate. You're welding it together layer by layer. And so on average, these layers are about 40 to 60 microns, and kind of a finished part. I'll get my workout in for basically what's that showing is kind of this part here. So you've got all the parts that are literally welded to this kind of build plate. So all metal 3D printing on this particular type of process, you're welding to a build plate. So all the parts come out here. So you can kind of see this. This is actually this build, but you see these kind of different designs. But at the end, you'd have to kind of remove that from the plate, and either through an EDM or a bandsaw or something like that, and finish all the parts off. So what that kind of entails, or kind of the event, why are people using this? Better resolution. It's fully consolidated once you kind of remove it from the build plate. Types of materials, titanium and stainless steel and things like that. And the resolution is pretty good. You're getting kind of pretty nice looking geometries. You can even do kind of things like threads and things like that. So I know it's hard to see, but there's a lot of opportunity with this type of technology. That's probably the most commonly used metal 3D printing technology in the industry. And those are for kind of finished parts, and that they can require machining depending on what requirements are, but in a lot of times, most use cases that are utilizing this technology don't have a lot of surface finish requirements. And the final one is called directed energy deposition. This is more kind of think like a robotic welder type of effort. So you're going to use bigger particles. You're depositing more material layer by layer, basically through a nozzle. And it's like you're decorating a cake, like you would see some of the standard filament material machines on the polymer side look like. You can either start with a wire, you can start with powder. But really in this case, you're making probably near net shape parts, but you can deposit a lot of material quickly. Things like cold spray, kind of other DED type of mechanisms would fall into this category. So the main advantage, you can deposit a lot of material. If you're doing bigger parts, that may be advantageous. You probably just have to come back with a machine head or kind of to help with dimensional accuracy. A lot of people are also using that for repairs. So if you have a big part that you need to repair, or just like oftentimes think like on an oil field, right? You've got a drill tip that needs to be repaired. You can use one of these to, hey, like we need this 3/4 of an inch kind of repair here. You take the line up the system, kind of repair that area, and then put it back into service. So oftentimes that's kind of a use case as well. So those are the three kind of different types of technologies. Um, just a description here, and anyone who wants the slides can get them. But I added a fourth here because there are some kind of metal polymer blends that are available, but nothing that I would put into kind of production applications. So kind of main takeaways here, kind of powder bed fusion with a laser, higher cost, generally slower builds because you're doing it kind of more smaller layers, but very good accuracy, kind of very good mechanical properties. DED that we just talked about, able to put a lot of material down, but surface finish needs a look afterwards. Good for larger parts and repairs. And then binder jetting. You can do large volumes, but you need to be cautious on dimensional tolerances, things like that. So other things that actually I think I skipped a slide up here. There we go. But I didn't really get into this initially, but like why metal 3D printing, right? We kind of go into like what is it, but the thought of like why are people even excited about this? Why are people looking at it? I think it really comes down to a handful of things. One is the ability to make very complex parts and consolidate uh, consolidate components, consolidate SKUs. So this is a really good example of kind of an actuator. This goes into there's an America's Cup boat, or kind of a big sailboat. But this kind of this actuator had 14 or 15 different components because of kind of the ability to really design and kind of remove channels, remove tubing and things like that, and just integrate in the part. They're down to one part. And so, yeah, maybe a higher failure mode, but you're not having to source 4 or 5 different places. So that's really a big use case. Low volume parts that you have to repair. So we do a lot of work on the defense side with the Air Force and others in the DoD. And so imagine a lot of the work that they have in maintaining a B-52 that was 70 or so years old, right? Most of the suppliers that made some of those original parts don't exist anymore. And they only need 10 parts a year or 5 parts a year. And so it's worth it for them to look at how to replace some of those some of those parts with newer technologies where the only inventory they have is the digital model. And if they have a multiple sites or distributed kind of manufacturing opportunities, that gives the capability of much more flexibility, less resilient reliance on outside sources and even international sources as well. So, and then kind of the other thing that on the material side, a lot of interesting work going on beyond kind of your conventional titaniums and aluminums and steels, the ability to really kind of produce graded materials and do kind of crazy stuff like this, where it's kind of a metal foam through both design and metal manipulation at each individual layer. That's more on the like probably closer to R&D, but we've seen some interesting applications of fused materials of copper and conventional metals to make kind of heat control and thermal control type of parts as well. But just to give you a scale, like, so these are a couple example printers on the side. So this is more on the directed energy deposition. So obviously you can see for scale, that's me in there. So you can do fairly big parts. This is a larger scale kind of powder bed fusion. So you'll be able to print kind of something that would approach like a rocket booster, things like that as well. So kind of going back to this, what are the design considerations, right? Everyone wants to know kind of what should I be thinking about if we're considering this technology? What are some of the red flags? And so the big thing that we could spend a whole day on is, like any technology. You guys are all manufacturers. You guys kind of do this on a day in, day out, whether it's injection molding, whether it's machining, whether it's casting. All these manufacturing processes have things they're good at and things they're not so good at. So wall thickness and um, how well does it hold the tolerance over 6 inches, 12 inches? Same things apply in additive manufacturing. And so there are a number of different considerations and directionality to how you think about it. I'm happy to share some design guides if anyone's interested that are pretty detailed and go through some of those. But each of the technologies has their own design considerations, whether it's not just how big can you make it, but hey, how long would a part like this take? So even something like this, which is, if you can see, it's probably about 6 to 8 inches tall. On some of the kind of the powder bed fusion, it's going to take could 8 to 12 hours to produce. Obviously, you're not producing one, you're probably producing 4 or 5, but just layer upon layer, doing that at 40, 50 microns and 20 seconds a layer, you get the idea of that the time it takes. But that's all automated. You can kind of leave the factory and go home, and it'll be done in the morning. The other thing that's important to note is some of these support materials or support structures, similar to like a FDM or polymer filament that you're probably used to seeing. Supports are often required for mechanical kind of support, but in the metal case, often it's used to dissipate heat as well. So most of these processes take place near room temperature, slightly above. So the chamber will be at about 90 degrees Fahrenheit or so, but obviously it takes more heat to melt metal. So the laser will be hot, but it's being put onto a cold bed of powder relatively. And so there's often residual stresses that are created and thermal stresses that are created that inform the design. And then last couple of things. So there's things to consider in terms of powder removal. So what I mentioned about this part up here, you saw that it was being built in a kind of full bed of powder. So once that's done, this is kind of hidden and you have to remove that powder. If you have a lot of enclosures or if you have kind of parts that have very small lattice structures or something like this, you'd have to make sure that you can get the powder out of that spot. And then there's obviously going to be kind of surface finish considerations depending on, hey, is it the top surface or the bottom surface, and other post machining operations that you might have to think about. So these we can go into all day, but just things that you can cover on top of mind. In terms of metals, I won't go into great detail on these, but it's a pretty, for the most part, you're starting to see more and more kind of standard alloys that you would normally see in casting and traditional kind of metalworking, but it's not all there. So in titanium, Ti64 ELI, very common, very well characterized. Cobalt chrome for other medical devices, Inconel for high temperature applications, and aluminum is probably one where not as many options as you'd see typically. Steel, there's a pretty good set of options, but you can kind of see the price below, right? Most of these are for kind of metal powders, for the pricing there. So you'll see a significant difference, right? And most of that is built into the challenges or the additional expense of making powders in a particular shape and spherical geometry and tolerance for how big the particle size distribution is. So the one nice thing about kind of a lot of the metal 3D printing is you can reuse any metal that most metal that was not processed. So if you have a bunch of powder that is left over from a build, oftentimes you can recycle that back into the next build and the next build and the next build. Not in all cases, but oftentimes we've seen 7, 8, 9 times powder being reused without major issues. Mainly because a lot of the the operations take place with under inert gas. So that's something I'll talk about next. But whether it's argon, whether it's nitrogen, you're not getting a lot of degradation on the or oxidation on the surface of these particles that would cause it to be somewhat challenging to make going down multiple recycles. And then kind of a number of different use cases, right? So I've mentioned some here, but just to give you a sense of where we see a lot of the applications are. Medical devices, medical instruments. We're working with a major hospital to look at mandible implants on that would go directly in the body for patient-specific matching. So if someone comes in, they are get a CT scan, we get their full geometry, and then in 2-3 days they're in the OR with a custom implant made directly for them with all their measurements and made from titanium that was 3D printed. So at scale, a lot of hip implants, knee implants are being made with the technology. All of these been FDA approved and gone through that process. And so you see a lot of the detail here, right? These surfaces are made specifically so that bone can grow into it, and it's and there's other benefits for some of the geometry capabilities of 3D printing, right? Because you have much more of these are geometries you wouldn't necessarily be able to machine in these little pattern areas as well. So other applications, I mean, a lot of work in automotive and space and that front. Some work in tooling to make 3D printed mold inserts with conformal cooling for injection molding or other operations, such as this, right? You wouldn't necessarily be able to machine that because it's not a through hole, but with 3D printing, because you're building layer upon layer, that's not a problem. And so you can build in different capabilities and tooling to make operations a little bit more efficient, a little bit more lower the cycle time and things like that. And then the big area now is on the tactile front with suppressors and other kind of firearm components as well. But a whole host of applications that we've seen, even things like for thermal management. I don't know if you can see that here, but again, a lot of kind of small features that you're able to kind of maintain cooling. But a lot of this again is high value, low volume parts that either are hard to machine or impossible to machine, in addition to kind of the maintenance and repair kind of space. So more of the brass tacks on kind of how much does it take to invest in the technology. Oftentimes it's not cheap. What we recommend is, if you're thinking about it, work with some suppliers, go through the technology, go to some trade shows, understand kind of the full costs and see facilities that have the technology. But a standard system kind of generally is around, like, the print area is about 11 by 11 by 10. Those are going to range in the $500 to $1 million range. There are some lower cost options now that kind of inch closer to kind of the 1 to 200K range, but you get kind of smaller beds, smaller print areas. There are multi-laser systems that allow you to go faster and kind of build parts more efficiently. And these are more the kind of laser-based systems, the binder jet and DED, probably on that order as well. Kind of 500K plus, maybe a little bit cheaper, but it's kind of larger industrial equipment is kind of the thinking here. It's not a kind of, hey, we're going to spend a couple $1,000s on an in-house kind of FDM printer. It's more of an investment capital expense that require other ancillary equipment. So I mentioned kind of inert gas that's often needed. So that's kind of a consumable cost that is required for operation. Oftentimes there's safety upgrades to handle metal powder or combustible dust. You should be familiar with kind of metal working, metal machining. So not only just to take parts off the bed, but to do any finishing or tapping of parts. And then in some cases, depending on the alloy you're using, it may require like a hip or heat treatment or stress relief process. And then, as I mentioned, powders range from $40 a kg to $200 a kg. So, if not more for more exotic metals. So, most of this has been used in the high end, but there are more and more opportunities of companies kind of either doing hybrid manufacturing with a combination of 3D printing and machining, as well as lower cost options. So kind of part of the accelerator program is like, hey, like we don't expect anyone, at least today, to go out and drop $1 million or even $500,000 on these machines without due diligence. So more of this is like, hey, like what's the state of the art? What are some of the materials that we're going for, and go from there. So last thing, just if you have any additional questions or anything like that, feel free to reach out. Last thing I'll highlight is we're doing a Grand Rapids tour of 3 different additive manufacturing users and operators. It's going to be September 30th, and the idea is to get people in some of these factories that are using the technology. This is mostly polymer based, but you get the idea of companies that have been investing in the technology, and seeing what they can do, and introducing you guys to some new suppliers. So that's it, and appreciate the time.
Well, really appreciate everyone jumping on and attending this webinar. Feel free to reach out if there's additional questions, or if you'd like to learn more about the accelerator or this roadshow to Grand Rapids. Thanks so much from Industry Labs.